All right. Okay, thank you everyone. I think this is a quite heterogeneous group, but perhaps I am the one coming from farthest away. So this is going to be kind of like a crash course on superconducting quantum circuits for quantum information applications. But before I start, I wanted to give an overview of who am I and where I'm coming from. So currently I work at the Barcelona Supercomputing Center, where we just started about a year ago, a new project on developing and building a superconducting quantum processor in order to bridge to the supercomputation. And the group is formed by two teams, theory team and experimental team. The theory team is led by Jose Ignacio Latorre, who has a very long experience in quantum algorithms. And now we're able to talk to each other, experiment and theory, and start to come together and design experiments to demonstrate certain applications. And this is a combination of work done at the Barcelona Supercomputing Center, the ICN2 Center, and the University of Barcelona. All right. So, and well, basically what I said, we build quantum processors and quantum algorithms. Having said that, this is the outline of my two lectures. I think it's a bit ambitious, so I'll try to get as far as possible for you to grasp, to get an idea about most things that are involved in superconducting quantum circuits. And the first thing I will mention, for those of you who have never heard of quantum computation, if there is anybody, and then I will quickly move on to the big part, which is the circuit quantization, and I'll explain several of the types of superconducting qubits you can obtain. And finally, I will get into details about how to control qubits and what prevents you from getting to the ultimate control. So first, the quantum computation. Very easily. So as I said, I want to focus on the superconductivity, so this part is going to be very rough and very sketchy, but just to give you the picture that in computers, we process information in bits, ones and zeros, and any circuit like this one consists of logical gates that process input bits and produce output strings of bits. And this information can be stored in a voltage, in an electrical switch, can be a flip-flop, a light intensity, magnetization, polarization, a DNA. So there's many ways in which you can build like a classical processor. All right? If you now go into the quantum world and you take a quantum object that has two states that you can identify, you can single out, and that you can control, read out with high fidelity, and put many of them together, then you can build a quantum processor. And a quantum processor has inputs which correspond to the quantum state of your individual elements, and they go through some black box that processes these states and produces a certain output. And this black box normally is written as a series of circuits of gates that couple these different quantum bits together. The ones that are vertical are coupling different of these bits. And finally, you make a measurement of your system. Now, every quantum bit has two possibilities, and they can be at the same time. So it's a vector in a two-dimensional space. It's a complex vector. When you have n quantum bits, n qubits, then you have 2 to the n state vectors. So that's a big Hilbert space. It explodes exponentially, very quickly. Right, and this is the power of quantum computation, being able to process such a tremendous amount of information with a very few quantum bits. But there's one caveat, and that's the measurement. So what do we measure in practice is just a classical variable. So in this cartoon, it says, how's your quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful and not even started. And then the question is, can you observe it? And that's a tricky question. So because if you observe it, you project your wave function into some given state, and that gives you some output. So in order to capture the statistics or your real quantum state, you need to do statistics, you need to repeat the measurement many times. But it is crucial that this quantum algorithm explores this gigantic Hilbert space. If your algorithm just has a very, very small amount of states being populated, this is going to be very inefficient, and probably it will be very easy to simulate classically. The really powerful quantum algorithms are the ones that really build up these gigantic vectors, which are the hard ones to find. Okay, so having said all this, so why would we ever need quantum computation? So let's take an example. This is the Mare Nostrum supercomputer, Mare Nostrum 4 in the center where I work. I invite you to visit it if you ever come to Barcelona. It's open. This has been built with 390 terabytes of memory. So this amount of memory is the same that you need to store 51 qubits. So you see where this exponential growth comes in. So if you want to simulate 100 qubits, forget it. Not this supercomputer, not all the supercomputers in the world combined would have enough memory to store a 100 qubit state. So this is where the quantum computation starts to come into play, when we have operations that require these gigantic states. But not all the operations are necessarily better in a quantum computer. There are some which are definitely going to be better. And I'm giving you some examples here. For example, simulating materials. And because this is a superconducting audience, I like to plot here like the critical temperature of different superconductors as a function of time. There seems to be a trend of going up, but it's not really known which material would be, if there is any, with a critical temperature at near or at room temperature, right? But if one could simulate a lattice of a crystal with a quantum simulator, then that would make life a bit easier. Another area where quantum computing could be useful is in the simulation of molecules in chemistry, chemical reactions. So here, all the pharmaceuticals comes in, and this is already very powerful to get interest from that big community. And another important area where there is definitely going to be impact, and to me this is the one that will come first, is in optimization. Optimization of things like traffic in cities, navigation, for example, the Curiosity rover on Mars that has to take many decisions in order to perform an action, scheduling, machine learning, and along, etc. So this is where I think quantum computers will come in first to say something better than the classical computers. All right, now let's jump to the circuit quantization. In undergrad school, we are told about quantum physics as being that which describes the domain of atomic systems, systems which are tiny, we cannot observe them with our eyes, and they satisfy the Schrödinger equation. On the contrary, larger objects like us or planets in a solar system, they obey Newton's law. So they obey a different set of rules which, in the end, quantum mechanics is compatible with these rules, but here we don't see quantum effects. There is an intermediate domain, which is perhaps also what most of you work on, but maybe you never thought about it in this way, which is mesoscopic systems, which are systems which are large, contain many, many atoms, and there are these larger particles, there are some degrees of freedom which are collective, and those degrees of freedom exhibit quantum properties. And these are artificial. We can design them, we can choose their properties. And this is very, very powerful, and that's why this field, this superconducting quantum computation is growing interest, because all the ideas behind integrated circuits, everything can be just plugged and played with these circuits. So it's important for quantum computation, but for many other aspects. But here I will only focus on quantum computation. Having said that, I should point out that there is a lot of work on quantum computation using single atoms, single ions, and there's a lot of work done in that direction. But again, I don't have time to cover it in one talk. Okay, so I was mentioning these degrees of freedom, these collective degrees of freedom. What are they? Let's take the simplest circuit you can think about, and this will be the classical harmonic oscillator. In a harmonic oscillator, we have charges in its capacitor, and then we have magnetic flux in its inductor. I can write down the Hamiltonian of the system as being the charge square over the capacitance and the flux square over the inductance. And this Hamiltonian resembles very, very much to the mechanical oscillator Hamiltonian. If I replace C by M, and that's mass, then I see that this is the momentum term. And if I replace L by K, then this is the potential of the oscillator. So and flux would correspond to the position. We know that the circuit exhibits one resonance, and this is the LC resonance of the circuit. Right? And classically, we understand very well this system oscillates. The energy is stored between the flux. It oscillates between flux and charge at the frequency of the oscillator. So this is all classical. Now let's take this device and we cool it down. And we cool it down to a temperature which is much well below the energy. I forgot an H bar here. Sorry. much below the energy of this oscillator. Now, the probability of this circuit being excited will go with this Maxwell-Boltzmann factor. And for a resonator of a few gigahertz, if I go to the few millikelvin, this probability is practically zero. So if I can cool down this device well enough, it will reside in its lowest energy state, no thermal energy. Which means there's no thermal fluctuations. And now quantum mechanics kicks in. The domain of quantum mechanics appears when I am able to remove all this thermal blurring. So these two variables, which are canonical variables in the language of Hamiltonian mechanics, now they become operators. They become quantum operators, and they have their commutation relations, and they also have uncertainties. And for the case of the flux, the uncertainty depends on the temperature and depends on the impedance of the circuit. And at zero temperature, this term goes to 1, and I am only left with this prefactor. And that's the quantum fluctuations of flux. So this variable, the flux in this inductor, which consists of the effect of all the particles in this wire, has the properties of just one single operator. And this is what I call this collective degree of freedom. If you're more interested in quantum circuits, I recommend you to take a look at this work by essentially Michel Devoret from the Yale group, which is one of the persons that has done most in this field. Okay, so now we have a quantum oscillator, right? So we know what the quantum oscillator energy system looks like. It's a parabola, and then the eigenstates are equally distant energy levels that each one of them corresponds to a quantum of energy stored, or a photon if you want, stored in this circuit. This circuit is already quantum. It has levels, and I know what their energy is. So is this a good qubit circuit? And the answer is no, because I cannot single out two of these states from the rest. Assuming I'm starting in its ground state and I want to come to the first energy state, I need to apply an external driving field which matches exactly this transition. The problem is that it also matches this transition and this transition and that transition, so I'm going to start to build a population of all the states. And that's not going to be useful for quantum computation. Therefore, I need something else. I need to introduce something in this circuit before this can become a quantum bit. And I didn't say that, but I also need, obviously, that the energy in the system does not decay very fast. So I need the quality factor of the circuit to be much larger than 1, which will also allow me to draw the width of these lines will directly depend on this quality factor. And for that, superconducting circuits are an obvious choice. In real world atomic systems, they have these very anharmonic spectrum. This doesn't look like at all a harmonic oscillator. So we want something that mimics, in a way, this spectrum. And for that, we need a nonlinear element. So here I come to the superconducting, strictly speaking, superconducting part. Maybe during the morning talks and this afternoon, this has been already said, but nevertheless, I wanted to give it a spin from the point of view of superconducting qubits. What do I think about superconductivity for qubits 101? I'm starting with a block of a superconducting material, and this block can be described by a macroscopic wave function, which has a phase and has an amplitude. And as I said before, this wave function has a phase so the phase of the wave function, and then the amplitude, which is related to the density, they satisfy commutation relations. Here is the wave function, sorry. So this phase and then this n here satisfy commutation relations. Now I have two blocks, and I want to put them very close together, and each one of these blocks has its own phase. And now this tunnel barrier will, in principle, prevent current, but we know that through the Josephson effect there will be supercurrents established between the two, which will depend on the phase difference between the two baths. This phase, this expression has appeared before, so I don't have to talk too much about it. I just wanna make it clear that we're talking about a current that can be measured with our apparatuses in the lab that depends on microscopic variables. So we have directly a microscopic effect that has a macroscopic consequence. These junctions, they store energy, and the energy is proportional to this prefactor, EJ, which is the Josephson energy, which is simply the critical current of this junction times the quantum of flux, which is this quantity, divided by 2 pi. And this energy is going to be very important for when I talk about qubits. The rest, at this point, it's not so needed anymore. Okay, so this junction has a constituency relationship between current and voltage. So if you have studied electrical circuits, you will identify this part of here as an inductance. And this is so-called Josephson inductance. This is exactly the expression of the inductance that this tunnel element contains, which is also going to be very important for making qubits. Since now this object has been so used in experiments and people draw it in circuits, it has its own electrical symbol, which is this cross. Sometimes you see it in a box, and I understand that means it also has, it includes its own capacitance, because a junction is a parallel plate capacitor, therefore it also has some charging energy. So we have a nonlinear element. This is a pretty nonlinear inductance, and it's also lossless in principle. It has some losses, but for now we don't worry about them. And this is one of the junctions we use typically in qubits. I didn't say it yet, but qubits are made of aluminum. Aluminum is like the silicon of quantum computation, and the tunnel junctions are always made with a shadow evaporation, so they always look like a copy of itself displaced in some direction. All right, so just a slide in case somebody has questions about fabrication. We do this shadow evaporation. Essentially, we create a polymer mask on top of our substrate, and then we come in with metal, and then we evaporate it. We oxidize between the two evaporations, and then we tilt our substrate in the opposite direction, and then we evaporate again. And then we obtain things like this. This is two junctions in series, so the current runs in this branch. And then we have these shadows on the side, which are, in principle, they are passive. In the end, they may add some parasitic capacitance, but it's quite small. All right, so now we have everything we need to build qubits. So let's build our first qubit. Again, we have this LC resonator, and the simplest qubit, this is, some people call it the hydrogen atom of superconducting qubits, is a slight perturbation of the circuit by replacing the inductance with the junction. And now I also change a bit the variables. Instead of charge, I'm talking about numbers of Cooper pairs. And instead of flux, I'm talking about the phase across the junction. But I think most of you are familiar with this. And now the Hamiltonian has this charging energy. And now all the capacitance has been absorbed by this constant. This is the charging energy of the capacitor. And this is the Josephson energy of the junction. And now phase is an operator. So we have these two energy scales. And this determines very, very strongly the type of qubit that you have. This circuit has a spectrum that is not anymore a parabola, but is a cosine. So this looks like that. If I quantize the circuit, very quickly you will realize that this is not harmonic anymore, and that's very good. That means we can now address 2 or 3 or any of these levels at will, if we have the way to excite them, to build a qubit. This qubit has a name. It's called a transmon qubit. It's an evolution of an older qubit, which was called the Cooper per box or the charge qubit, right? And it was detailed in this work, which I strongly recommend to take a look at. So let's take again this Hamiltonian, because I mentioned these two energy scales. So if I make a ratio of them, the Josephson energy over the charging energy, and I plot like a log scale, on the left, which means charging energy larger than the Josephson energy, we have the charge qubit, the Cooper per box. This was the very first superconducting qubit that people used to demonstrate coherent control. Unfortunately, in any circuit, there is charge noise. And charge noise is really too bad. And these qubits were terrible as a qubit. So it was a good demonstration, but you could not do much more. You could detect a lot of charge noise, essentially. It's a good charge sensor. On the opposite extreme, we have phase qubits. These are also by now discarded as a candidate, but in the early days, people used them a lot because these are very easy to design. These are very large junction in a superconducting loop, biased. And the junction in this tilted washboard potential is essentially like a tilted washboard that is tilted in a way that only a couple of levels reside in this well. And that is a qubit. The problem is that you need very large junctions. So that means you need very large EJ. And that puts you in a place where you are very sensitive to flux noise and microscopic defects in your junction. So these qubits were never very good. Their coherence properties were always below the other ones. And finally, we come to the middle ground, which is where this transmon qubit resides, the one I just described, and also another one that I will explain in detail, which is the persistent current qubit or flux qubit. And they both are close to a ratio of about 100. This seems to be some kind of optimum for circuits. So you see, it's very important that this ratio is around 100 if you want to have a good qubit. Now let's go to talk a bit more about this transmon qubit. Again, I plot here. This is the actual potential calculated in this work. This is the wave function of the transmon for the different states. So we have instead of a harmonic, we have this cosine potential, and these eigenstates of this qubit, even though it's a charged qubit, it's not anymore a pure charge qubit. The point is that because of this charge noise, charge qubits were useless. So people decided to put a large capacitor across the junction. And in this way, large capacitance decreases the charging energy, because charging energy is inversely proportional to the capacitance. And by doing that, they increase this ratio, EJ over EC. You see what is plotted here is the wave function of the qubit in the charge basis, in the number of charges. And for EJ over EC 10, small, everything sits around 0. So here, that means the wave function is more well approximated by a pure charge state. As EJ over EC increases, now you see that we're getting distributions of these states. That means the eigenstates of the circuit are superpositions of charge states. So our two states or n states here correspond to a different distribution of charges, but as a superposition. This is what these qubits look like in reality. I said they have this big capacitor. That's this finger structure that you see. And in the center, there is the junction. You cannot see in this picture very well. In fact, it's a loop. It's a squid. So you can also use squids in this case. And now this is basically the circuit. I draw it here in a cartoon. I have a squid, so I can modulate the effective size of the critical current, which modulates the EJ energy. And that modulates the energy of this qubit. So I have a tunable energy. This is a spectroscopy of one device I took from this paper, from the ETH group, where they observe as a function of this flux threading this loop. And this is the excitation energy in gigahertz. This is the lowest energy state, the ground to first excited state. And they also observe the second transition from ground to F state. One comment I need to make about this qubit is that you see these transitions are almost proportional to each other. Proportional would be exactly harmonic, but they're slightly off by a few percent, 3 to 5%, but that is enough for you to be able to address this one or that one. And that is crucial. Otherwise, this qubit would not be useful. Actually, I have it here explicitly. So this is again this effect of this shunt capacitor of this qubit. This is what the energy levels look like for the charge qubit. You can actually identify parabolas here, which corresponds to the charging energy, the charge energy, which is proportional to the charge square. And because of the Josephson junction, you open up these gaps. And then this gap here would be where you operate your qubit, your charge qubit. But as I increase EJ over EC, these bands become flatter and flatter until EJ over EC equals 50. This is pretty much flat. That means the energy splitting does not depend on the offset charge in this qubit. And that means the qubit is insensitive to charge. And that's the energy of this excitation. This is the plasma frequency of the junction with the shunt capacitor defining the EC. And then the difference between the first and the second transition is this alpha parameter, which people call it the enharmonicity. And for this device, it equals the charging energy. So if you make this capacitor bigger and bigger, the charging energy will be smaller. And at some point, the transitions will be indistinguishable. And that's where you don't want to be. So the capacitance should be large to suppress charge noise, but not too large. So there is some intermediate regime where things work very well. And this qubit is now like the workhorse of almost every group, every large group in the world, because it's very simple to fabricate. You only need one junction. The energy transition only depends on the square root of parameters. That means that gives us some insensitivity to parameter fluctuations. And the coherence times are very good, as I will show in a moment. Now let's switch to a different type of qubit, the flux qubit. So this one is a bit older, but nevertheless it's still very, very active. To understand the flux qubit, since most of you know about superconductivity, I wanted to take more like a superconducting picture of how to get this qubit. So let's start with a superconducting ring that is threaded by a magnetic flux. This ring, as we know, it has this wave function, and then the phase around the loop is quantized. It quantizes the flux. So because we have to come back to the same place, so depending on the number of flux quanta that are trapped in the loop, that will change our total phase. But this number is fixed as we cool down the circuit. If we now introduce a junction in the loop, the phase will be changing as we increase the external flux. This is a kind of like a semi-classical picture, but I think it conveys the message. This plot here shows the circulating current in this loop as a function of external flux. And so the current is ramped up as I increase flux, until it reaches a point that is approaching the critical current of this junction. At that point, the circuit lets a new flux quantum in the loop, and then that reverses the current, and then I'm back, so I stay superconducting all the time. And in this way, as I ramp up flux, the circulating current is jumping. But at this point, when it jumps, it's classically degenerate. So this is at half a flux quantum. The two currents, clockwise and counterclockwise, have the same energy. Now, if I talk about